Hello students, today we will find the magnetic induction at a point on the axis of a coil which carries a current I. So what will have? Current that is flowing through the coil. The radius of the coil is also known to us. If you have n number of turns, that also is fine. And you have this axis. This is the axis of the coil. Now at a point here, somewhere from the center, along the axis, at a distance say x from the center of the coil, you have to find the magnetic induction. Earlier our attention was to find magnetic induction at the center of the coil. Now it is away from the center. You move along the axis and find the magnetic induction at any point. Let us derive that expression. I will just help you first understand the diagram. This is the plane of the paper. My coil, I'll keep the coil not like this, not on the plane of this paper. I'll keep my coil like this, vertical plane. The coil will be in a vertical plane. Okay, and this is the axis. I will find the magnetic induction at any point somewhere along this axis. Suppose this is the point where I have touched. So this is the point where I have to find this point where I have hold this. So this is the point where I have held the axis. There I want to find the magnetic induction. Let us say that this distance of the point from the center is x, and we will think one more interesting thing, that this is the coil, this is the circumference, or you can see that to any, if I choose element over here, then that element, the direction of the ideal, that is the element direction, say this is the situation. If I choose an element here, or here, or here, or here, or here, something like that, I have to move around the circumference to choose elements. Anywhere I choose, suppose I choose here, the center of this element to the point, suppose this is the point where I want to find the magnetic field. This is the point. If I join a line from this element to this, it will look something like this. Something like this. Like this. If I choose element here, it will look like this. So from each element, I have to join to this point. That is the R vector. So this is R vector. Now, I want the angle between this DL element, which is the tangent to the circumference at any point. Suppose at this point, this is the tangent, this is ideal, and what is R vector? The center of this element to the point where you want to find the magnetic field. So this is the R vector. This is the ideal vector. This is the R vector. You can see now, this R vector and ideal vector are perpendicular to each other. Whenever you choose the element, if I choose the element, the DL is like this, and this R is like this, it will be always 90 degree. This line is 90 degree to any line over here. this is always 90 degree. Whether I choose here or here, this is always 90 degree. Tangent and this tangent, and this is always 90 degree. So that will help us to find the magnetic induction. So this diagram that I explained you, that I will draw here. So I have to draw a coil like this. So this is drawn something like that. This is like this situation. That the coil is like this. The center, and this is the axis. I want to find the magnetic field at this point. Say P. This distance is x from the center. This point is P. Okay. Now the current flowing is I. Let us say the radius of this coil is R. R is the radius. Now I choose an element just like this here, somewhere here, this position or this position, any position you can choose. You have to choose everywhere. So let us say at any position here I have chosen. Okay, this side. Then if I choose from here this element, then it will be like this. This is the ideal vector. And from the center of this to the point, I will join a line. That is R vector. So this is R vector. Okay. So this is my R vector. What is the angle between this element and this vector? So this is the axis, something like that. It is always 90 degree. It's always 90 degree. Wherever you keep, it is always 90. This and that will be always 90 degree. Because if I have this line, if I rotate this line, you can see that this line is always perpendicular to this length. So for this line, the coil is like that. So element is like this. You can see this is 90 degree. It's very 90 degree. The coil is like that. I've taken one element here. It's 90 degree. If the element is here, then this is also 90 degree. So what is happening is this is actually rotating. You can see here that to this point where I want to find. If I move around the coil, then I have to move like this. Because with element, the R is also fixed. R also has to move like that. So for any situation, now this completes the loop and this remains always 90 degree. This is something like that. Always 90 degree. So theta is 90 degree. Suppose this length, okay, this is R we have taken, so radius we can take A. Okay. So I will write all the symbols that I have used. A is the radius of coil. R is the position vector. Here the position vector means this distance of the element from the point. Distance between x is the center point. Now, one more important point. Again, this is my ideal vector. Suppose this red part is the ideal, the element I have chosen here. This is DL element, which is here also here. If I multiply I, that is current flowing, this is called ideal element, current element. It's a vector quantity. And the direction is shown as like this. This is the axis. The point is here. This is the point. So I will have to draw a line, the R vector, from this element to the point, like this. The axis is like this. I have to draw like this, from here to this point. I'm not changing this point, I'll keep the point constant, like that. Okay. Now, the angle between this R ideal and this R vector is 90 degree. So this angle is 90 between this element that comes out, that cannot be drawn on this diagram. This is like this, and this is 90. Now, what would be the direction of magnetic if it is like that? R vector, this is your ideal vector. Ideal cross R gives you the direction of the magnetic induction. So this and this, you can see here. First, put your right hand. This is cross product. So right hand cross rule or palm rule. First vector in this ideal direction. Sweep the fingers towards the second vector. Second vector in this direction. So this is the direction of. So this is the direction of dB. Okay. This is the element. This is the R. Then I'll show without this also. This is their element. This was our R. This is our axis. You can see here. This was axis. And this was the R that was connecting this. And B is something like that, BV. As you can see here, it's like this. Like this. This is perpendicular to this and also perpendicular to this. That is the concept of cross product, that this vector is perpendicular to this as well as this. So any vector lying on this plane, this will be perpendicular to this two. So now this is the vector. If I write that this angle is theta. Okay. So where I have chosen the element, here I'll have to take all the elements like that, from here to this point, 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 this point. So from the axis to the point, the angle, suppose it makes is theta. Okay. The axis and the element makes an angle theta. Okay. Now this contribution of all the elements towards magnetic induction will be in this direction only. Why? Because it is a coil carrying current in this sense. I hold it like this. This is the direction of B, in this direction. So each element will have contribution from this direction. Therefore, I have to resolve irrespective of the element I choose in these two directions. The vector has to resolve along these two directions. One is this direction, another is this direction. In doing so, then I have to resolve this vector dV along this line and this line. I must know the angle it makes with any one of the two sides. We all know that this and this makes an angle of 90 degree. This and that also is 90 degree because it is the outcome of the cross product of ideal and R. So you can see that if this is theta, this angle will be 90 minus theta, because this sum of the two should be 90. This angle plus this angle, the sum should be 90. So this theta, this is 90 minus theta. Again, if this is 90 minus theta, this is 90. So if this is 90 minus theta, this should be theta. This should be theta. So this angle is now also theta. This angle is theta, that angle is theta. So this theta is dV. So this will have two components. This component is dV cos theta. This is dV sin theta. So if I move to another element, if I move to from here to move here, I move. Then also, so for this side, this half of this coil, wherever I choose element, that vector will be in this direction. And for any element I choose on the opposite side of this coil, this side, for this side, this half of this coil, the magnitude will be in that direction. For other half, here, this side, you can see if I choose element here, this is dl, this will be my r, ideal r, it will be something like that toward this side. Now earlier it was this side, ideal r. Now ideal is this is ideal, r is here, so I'll bend like that and it will be like that. That is ideal is going into r, it will be something like that, ideal r, like that. It is like this, it's like that. So for this element over opposite to this, it will be like this, dv will be like this. Again, if I resolve this into two components, then dv sin theta and dv cos theta. What is happening is, for every pair of elements on the diagonals or on the diameters, opposite end of the diameters, I'll choose element here, then here, then here and here. So for every pair of elements on the opposite ends of the diameters, the horizontal components will add up, will be always in this direction, and the dv cos theta component will be one half, it will be up direction, the other half will be down direction. For the element which is here, for this element, this is the dv cos theta. For the opposite end, if I choose an element here, for this it is like this, for this it will be like that, so they will cancel out. Similarly, if I choose an element here and here, or anywhere here and here, so they will cancel out. Every pair of the vertical components will cancel out, the horizontal components will add up. So I'll do one thing, I will integrate separately, because the dv is a vector quantity is changing from as you change the elements, so you cannot directly integrate from 0 to 2 pi r. You cannot do that because it's a vector and the direction of vector is changing. Though its magnitude remains the same, the direction is changing. Therefore, for this element, we integrate this from 0 to 2 pi r to get the total contribution by this coil along this direction. If I integrate this, obviously I will get 0, then that will give you the contribution along this vertical line. Then I will take the vector addition rule, square of this plus square of this root, but because this is 0, so this is only the answer. So I'll just first write the answer by solving this, then we'll see. Now the this is dv sin theta, this is dv sin theta. where A is the radius of the coil, dV sine integration. But what is dV? dV general formula is mu 0.4 pi ideal sine theta. But here that theta is something else and this theta I'm writing is something else. There in the diagram, theta is the angle between the R and axis. That is theta. But in your expression of ideal sine theta, the theta is the angle between the dl element and the R vector. There is a difference. So ideal, that part of sine theta is 1, but the sine theta will remain divided by R square and you integrate it from 0 to 2 pi A, where A is the radius. Now mu 0.4 pi common out, I is common out, R it's same common out, dl integrate and sine theta. Now we have to write sine theta in terms of the other variables. Now if you look at the diagram that we have drawn earlier, that if I take this right angle triangle, okay, this R square is A square plus X square. R square is A square plus X square. So, and sine theta is A by R. The perpendicular upon the hypotenuse, A by R. So I write A by R here. So this R, A by R, this R comes out, becomes R cube, because it is my, now A remains outside, but because A is also constant. A is the radius of the coil, also can be taken out, R is also taken out, sine theta itself is a constant. And to change element, this theta will remain same with respect to the axis. This angle is not going to change. You can see here, okay, this is the point, this is the axis. The axis has to rotate like this only. So this angle is not going to change. You can see here, the angle will remain same. This angle is not going to change. So therefore, sine theta is also a constant taken out, which is A by R. So this is A by R cube. dl integration from 0 to 2 pi A. That gives us mu 0 upon 4 pi I A upon R cube into 2 pi A. Next page, what we will have the final expression. B on the axis of a coil is mu 0 upon 4 pi 2 pi A square. 2 pi A square comes out. I also is there. R cube is also there. Now, what was the triangle? The triangle is like that. This is theta, this is R, this is X, this is A. The radius of the coil. Now, this R is basically A square plus X square. R is A square plus X square root. Pythagoras theorem. Sum of the side square is equals to the hypotenuse square. But here it is R cube. That is, if I take the cube on both sides, this will become A square plus X square to the power 3 divided 2. that I'll write here. So the x is equal to 4 pi 2 pi a square I divided by a square plus x square to the power 3 by 2. This is the final expression. Now, if the coil has n number of turns, you multiply n over here. So the dx is, this is for one turn of the coil. For n number of turns, 2 n pi a square I divided by, this is the final expression where n is number of turns. This is the final expression. If the coil is of very small size, okay, if the coil is of very small size, then the radius of the coil will be very much less compared to the x. X is where the point lies on the axis. The coil is very tiny, the radius is small, but this x is very large. So in that case, we can neglect a wherever is possible. That means in multiplication you cannot neglect. You can neglect here. So for short coil, B axis will be mu naught 4 pi x cube. This will be 0. This 2 will cancel. It is x cube. This formula is used. Okay. Again, one more thing you can check it out, that if the point is here at a distance x from the center of the coil, if I bring this point closer and closer and closer and closer toward the axis and finally at the center, if this point is brought at the, and kept at the center, then x value will be 0, because x arises because of the distance of that point from the center. If that point is on the center, then there is no distance of separation, so therefore x is 0. If you put x is 0, then this expression will reduce to what? Let us also see. This expression will reduce to what? B expression that I have told you is on the axis for a big coil. Which is the one? If x is 0, cancels gives you a that means this is similar to the result that we have got. If the point is taken from axis to the center, then the expression for magnetic field will be equal to the magnetic field at the center of a circular coil. And earlier we have derived that the magnetic field at the center of a circular coil is 0.4 pi 2 pi ni by r, where n is the number of turns. For full circle, the angle is 2 pi I by. If a is the radius, if r is the radius, then you could take right r. So this justifies, this is correct, this expression is correct. Once you make x 0, once you make a 0, there are two conditions that I just told you. If a is 0, this expression, so short magnet, short coil, if a is 0, then this becomes So these are the things you remember. And pi a square is the area of the coil. So it's pi a square. But why I have kept this separately? Because this is nothing but the area of the coil. So to remember this, you can remember like this. The axis is 0.45 is always there. 2 NIA, 2 NIA. On the axis is always NIA divided by whatever is that the distance a square plus, where a is the, here also is the area 2 NIA. We will later learn that in magnetic induction that NIA are the dipole moment. Okay, so in comparison, that will be equivalent to the magnetic dipole moment I into A, that we will learn other day. So this is the final answer to this question. So this is the final expression, and these are the expressions under such conditions. Okay, thank you.